So let's go ahead and get started. So we're going to have our second exam on Thursday. So I talked to a couple of you guys and we're panicking. The irony of this is the book that I learned this out of was called Don't Panic. So I kind of tried to take that to heart. But I'll try to tell you guys the same thing that tests are important. It's important to do well on them, but it's not always as important as you build it up to yourself for two reasons. One, the exams in this class in particular are only worth 10% of your grade, so it's more important to be on top of things and coming to class and doing the classwork. But two, even for the classes that the exams were a bigger deal. So you might have had like a English class or a math class in high school you got really anxious about the exam for. At this point, who cares, right? I mean, that's in the past. Took an exam like 4 or 5 years ago. It's not as big a deal as you might make it out to be. So I don't want you guys to get stressed. Even I'm weird like this. I think you guys should try to have a little bit of fun in the exam because we've been working really hard to learn this material, and this is an opportunity for you to say, yeah, I understand this, and I get to show that. So to start out with, I just want to lay out all of the material that's going to be on the exam. I'm going to be doing a live stream tonight and a live stream on Wednesday night to go over this in more detail. But just to give you an idea of what all of the material is going to be, the first topic we had was Gauss's law. So actually, let's write this one. Let's write this one right here. So this is Gauss's law. So when we did Gauss's law, we saw that there were 3 types of symmetry that we could have. So 3 symmetries. So these were our spherical, our cylindrical, and our planar. And then there were 2 types of materials. So we had insulators and conductors. Now, the key to dealing with insulators and conductors was to talk about what the electric field was and what the charge inside was for those 2 particular situations. So for our insulators, we could say that Qn was equal to the integral of rho dV, and for the conductors, on the inside of the conductor, the electric field is 0. Now, since I wrote Gauss's law here, it's important to write that down as well. So this is the integral of E dot ds is equal to 0. Okay. So first question is going to be something like this, but we also saw that a lot of the material that we go over in this class, it carries over to other areas, and so that's to say Gauss's law was really important for understanding how to find capacitance of systems. So the next topic was capacitance. And in order to find capacitance, again, we had the same 3 symmetries that we used with Gauss's law. The only thing that we really added on top of this was to say that the definition of the difference in electric potential is equal to the negative integral from R1 to R2 of E dot dl. And that by definition, the capacitance C is going to be equal to the absolute value of the ratio of the charge on some conducting system to the difference in electric potential between those 2 plates. And really, like I said, everything that I did with capacitance here carried over from what we did with Gauss's law. Additionally, we were able to prove that when we have capacitors in series and in parallel, that they add in a particular way. So capacitors in series added according to 1 over CEQ is equal to 1 over C1 plus 1 over C2, and in parallel these capacitors are going to add CEQ is equal to C1 plus C2. Okay, so this is already actually half of the material. The next piece that we need is resistance. So for resistance, We built this up from the ground level just like we did with capacitance, and so this equation here, again, is going to be important. We also said that inside some conductor that's like not a perfect conductor, but one that has some resistivity, we can say that the electric field is going to be equal to rho times J, where J is the current density vector, and we can relate the current density vector to the current by saying that the current is equal to the flux of the current density vector. Okay? Couple more pieces that we had. So this was what was called the microscopic form of Ohm's law. The macroscopic form of Ohm's law says that V is equal to IR. And then we were able to show,
So for resistance, is that only used with conductors?
Yes, and it's important that this rho, and it's not when I talk about Gauss's law on conductors, these are perfect conductors. These are conductors that have resistivity of 0.
Okay.
When I talk about resistance, it's some material that has some resistance that's not perfect, so current's allowed to flow through it. So that's why I say that when I'm using the microscopic form of Ohm's law, it is a conductor, but it's not a perfect conductor. It's a conductor that has some resistivity. And the other important piece, I'll get back to you in a second, is that this rho is resistivity and this rho is charge density. So it's historically unfortunate that we have these two symbols on this same test that mean two different things, but you need to take in consideration that this is charge density and this is resistivity. Yeah. Do you have another question?
Yeah, how do we know when like a capacitance is in series or parallel?
It's to think about when something's in series. So think about like if you're doing your laundry, right? You have two laundry machines. If I do my laundry in series, I do it in one machine and then I do it again in the same machine, right? So it's sequential. I go same machine, same machine. In parallel would be I do both at the same time in two different machines. So to give you an idea what I mean when I'm drawing this analog, if I have two circuit elements in series, if I'm some charge and I'm going around here, I go from one to the next. This is in series. Whereas if it's in parallel, and I'm doing this for resistors, but it doesn't matter. It's just the symbol. It's different. In parallel, I get to some junction here, and I have a choice. I can go here or I can go here.
I guess I was confused about when we were doing this stuff with like cylinder.
Oh, okay, sure. So if I had some geometric system instead of the circuit diagram, it's really the same idea. So if say I have these plates like this, is this going to be series or parallel?
Series.
This is series, right? Because if I want to find the difference in electric potential between here and here, I only have one choice. I can go from here to here to here. But if I do it lower or somewhere else, it's really the same process. I'm going from this plate to this plate. But the example that we did here was we had some resistivity epsilon 1, some resistivity epsilon 2, or epsilon 1 and epsilon 0. The difference here is I can go through this material, I can go through this material. And that's kind of the same thing if I drew this in terms of a circuit diagram. Make this squeaky. I have a choice of which capacitor I go through, right? So that's really what's meant when I talk about whether something's in series or parallel. You can think about it in terms of the analog that I talked about. If you're doing your laundry, if you're doing it in series, I use the same machine multiple times. If I do it in parallel, I can use multiple machines all at once. Okay. Other questions? Okay. So the last thing that I want to say about resistance is how I can add resistors in series and parallel. And that's to say that in series, I'm running out of room here. Can you guys see this in the back? Can you guys back here see this? Okay. So in series, resistors are going to add just the equivalent resistance is equal to R1 plus R2. And I don't know why I have all this extra space that I don't need. And in parallel, this is going to be 1 over RAQ is equal to 1 over R1 plus 1 over R2. The last thing that we saw was that we went through this process using the microscopic form of Ohm's law and the definition of the current in terms of the current density to find what the resistance of some system is, but we could also do this in terms of some infinitesimals to say that dr is equal to rho dl divided by a, where this a parameter comes from this dot product. This is the resistivity that we had from our microscopic Ohm's law, and this dl comes from here. Okay? Any questions about this? Okay. So the last thing that we're going to have is the time-independent circuits. And this really just boiled down to 2 equations, and this, again, it comes from, this is kind of the mother of all equations on this exam. Everything talks to this equation in some way. So this is to say that the integral over some closed loop of E dot dl is equal to 0, so that's one equation. This is our loop equation. And then the second equation was the flux of the current density out of some closed surface is going to be equal to the time rate of change of the charge contained in the surface, which in the case of time-independent circuits, or actually basically everything that we're going to do is that minus dq dt is equal to 0. Okay? And this is everything on the exam. Other than understanding these what these equations mean, it's just a matter of practicing these. We spent 3 days doing this. We spent 2 days on this, 2 days on this. We're doing the second day of this today, and then we're also going to do that in recitation. So I think having seen it now, it probably looks a little less scary than it did before, maybe. Okay. Any questions about this? Okay, so now what I want to do is I want to go through Sure.
Sorry.
Yeah.
So like for when we were talking about Gauss's law and we were talking about like conductors, so we can never use that Qn is equal to rho dl equation for conductors ever?
This is a dV here, sorry.
Yeah.
This is, yeah, it's just kind of on the line. Let's get that around.
Remember there was a question you were asked about the charge density inside a conductor?
So it's when you find charge densities relating to conductors, it's not the volume charge density, it's the area charge density. So if I had say I had some point charge that's surrounded by some spherical shell, that's a conducting spherical shell, I can find what the area charge density is. So here's some shell. Let's say that there's no charge on here initially. I can find what the area charge density is on this. If this is some inner radius of A and outer radius of B. Because Gauss's law is going to tell me that the electric field on the inside of here is going to be equal to 0. That means that at the inner surface at a radius A, there's some charge minus Q, and at the outer surface there's going to be some charge plus Q, because I'm saying that this is initially uncharged. Okay. Now, to answer your question about when we can talk about charge densities for conductors, this is sigma. It's not rho. So sigma, by definition, is the charge per area. And this is just to say, well, what's the charge spread on the inner radius here divided by the total area? So if I wanted to find what sigma A was, sigma A is just going to be minus Q divided by 4 pi times A squared. Okay.
How can you like assume it's minus Q?
Because, so why did I say that this was a minus Q here to start with? It comes from the fact that E on the inside of the conductor is 0. And if E on the inside of the conductor is 0, and Gauss's law says the integral of E dot ds is equal to Qn divided by epsilon naught, left side is 0, right, because E is 0. That says Qn is 0. But in order for Qn to be 0, Qn is going to be equal to the charge, I'm just going to say Q origin plus Q at A. right? Because they only have the charge at the origin and the charge at the radius A. And then because of this, and this is equal to 0, I know that Q at the origin is equal to plus Q. That means QA has to be minus Q. But this is just going through an argument with Gauss's law for conductors, for saying that because the electric field is 0 on the inside of the conductor, Qin is 0. Qin can only be this charge at the center plus the charge at the surface because this is a conductor. And then that says that QA is equal to 0. Okay? Other questions? Okay. Okay, so let's go ahead and look at these circuits. I don't want to spend too much time on them, but I'll set up the equations for them. I won't solve them explicitly. So the first circuit was something that looked like this. I'm going to have you guys talk me through how we want to do this. So once I set everything up. So this is our V, this is C1, this is R4, this is R3, this is C2. Okay? R1. Okay. So the first thing that we want to do now that we have this labeled is to put in some currents. Right? We have to label our currents, we have to label our charges. So what's somebody just name a current through one of the resistors that we want to put on here. I1, where are we going to say I1 goes? Through R1? Yeah. Okay. This way through R1. So that's one. What about another one? R2. We want to say that one goes through. Okay. Up or down? Down? Okay. So I2. How about another one? I3. I heard an I4, so how do we want to say I4 goes? Okay, let's say I4 goes up. You can do this however you want. It doesn't matter. I'm just using what you guys are saying. And then somebody said something about I3, right? I3 up or down? Down. Down. Okay. I3 goes down. Okay, charges. We need to put some charges on the capacitors. I think we should call this one a Q1 and a Q2, right? That would seem to make sense because we have C1, C2. Do we want plus Q or minus Q on the top? Plus Q. Plus Q, okay. Plus Q1, minus Q1. How about C2? Plus Q, minus Q on plus Q on the top. Plus Q on the top. Okay. Plus Q2, minus Q2. Okay. So now we have everything labeled here. Now what we could do is we could either start by drawing loops or we could do a junction. I'm going to do a junction first. So where could we put a junction? Where could we put a junction?
Top in the middle.
Yeah, right here?
Yeah.
Yeah, let's do that. Okay, so based on this junction, we know integral j dot ds is equal to 0, which says that really the sum of the current in is equal to the sum of current out. Okay, so what does this say for this particular setup that we have? What's the current, or what's the sum of currents going in? So we have I1
Plus I4.
plus I4 is equal to I3. Good. Now, we can say something else here, and it has to do with I4.
It's 0.
Why?
Because it's going right to the capacitor.
Right. This is steady state, and if we're in a steady state, that means that the capacitor is fully charged, which means there can't be any current flowing here. So this actually says that I4 is equal to 0, which says that I1 is equal to, is equal to I3, okay? Let's draw a second junction. Where do I want to put my second junction? Yeah.
So this is something I have a problem with. Is it automatically 0? Like, for example, the current, it's going to go through resistance 4. In this case, before it goes to capacitance 1.
Right.
Is it 0 at resistance 4?
Yeah. The capacitor here takes precedence over the resistor when we're doing time-independent circuits. If we do time-dependent circuits, which will be on the next test or on the final, then it does matter. But we're not going to worry about that here. There's a capacitor here. There's no current flowing through this at all. Okay. All right, so I want to put another junction here. Where can I put my other junction?
Between I3 and I2.
How about where R3 is going into the box?
Yeah, I think you guys both said the same thing. This one right here, right? Okay, so what does this one say? Now there's actually something else we could have labeled here that we didn't, but we still get the same idea.
Is there a fifth current?
Yeah, we could have said that there was an I5 here, right? We could put that there. In which case this is going to say I in, which is I3, is going to be equal to I2 plus I5, right? But why was I was a little bit lazy before and I didn't ask you guys to put one here. Why don't I have to put an I5?
Because it's 0.
Yeah, it's 0. Okay, so this says I3 is equal to I2. We can put that here. And from now on, I'm just going to call any current just I. So actually, all of the currents here are the same. Okay, so we've done our junctions. Now, how many unknowns do we have here? We've reduced it in a way, right? We've gotten rid of some of the unknowns because previously we said that there was some unknown I1, some unknown I4, I3, I2. We reduced all the currents down to just one unknown. So what other unknowns do I have left?
The charges on the capacitor.
The charges on the capacitor, right? So I still have some Q1 and some Q2. And I have I. So this one's already taken care of. I've gotten I. So I need 2 more equations. I need 2 more equations. So how can we draw our loops here?
You can do whatever you want.
Yeah, I can do whatever I want, right? So let's do this one. Let's do that one. And whenever you have the opportunity to, you want to do this in such a way that it's as simple as possible. And actually, I need 3 loops actually, because I have 3 unknowns, right? So this isn't taken care of yet. I've condensed all of the currents into just this one, but I do need 3 equations, right? So this is what I'm going to call loop 1. This is what I'm going to call loop 2. And I'm going to use a little bit of, it's not really a trick, but it's something that will make the algebra easier later if you realize this. I'm going to draw this loop. And it might seem like, you might be like, and somebody just said it, I heard it. Why would you know to do that? Well, somebody did it. Why did you do it? Yeah.
Just because, like, you can skip the capacitor if there isn't any charge
Right.
through it.
Right. So the reason why you would want to draw this loop is the only unknown that I have in it is the current. Right? There's no capacitor. So ultimately, when I try to solve this system, this equation is already decoupled from everything else. Right? I can solve that one really easily. So let's actually start with that one. I'll show you exactly why I did this. So this is loop 1. So for loop 1, the integral around loop 1.
Label something loop 1.
Oh, did I? Oh, sorry. Well, make that one 2 and this one 3 then. Okay. Dot dl is equal to. Now let's go around the loop. Now, I'm not gonna break this apart in every little piece. But we understood that we should do that in principle. Let's start here. What's the first thing that I see when I'm going around this loop? I see the battery. Is this going to be plus or minus? Minus, right? Because I hit the negative terminal first. Okay, so negative. Now I'm going this way, same direction as the current. This is going to give me a contribution that says what? Plus I1 R1, and we're already saying that all the currents are the same. I'm just going to leave this as I times R1. Okay. Next piece. Plus I or 3. Next piece. Plus I or 2 is equal to 0. And now you can explicitly see why this was a good loop to choose, because this only has the current in it. And so if I wanted to solve this, this would just say that the current I is going to be equal to V divided by R1 plus R2 plus R3. Okay. Is everybody okay with that? Okay. Next loop, we'll call this one loop 2. So integral around loop 2 of E dot dl is going to be equal to, again, I'll start right here. This is going to give me a plus V.
Why would it give you a plus V? It seems like you're going in the same direction across it.
Yeah.
It should be a minus V. I was checking to make sure you guys are paying attention. But you see, this should be minus V, right? I'm going around this way. I hit the minus first, right? Hit the minus first, minus, okay? Then this gives me a plus IR. And then this is going to give me what for the capacitor? Plus Q1. Plus Q1 divided by C. And then I'm back here, C1 is equal to 0, okay?
You have to do R4.
Why don't I have to do R4? In principle, you could. Yeah, because I could put, this would be like a minus I4 R4, but we already determined that I4 was 0. Yeah, okay, good. Last piece, this one. So this one's, it's a nice easy loop here. So integral of E dot dl for loop 3 is going to be equal to, let's start here. Let's start here, okay? Going around the loop, what do we see? C2. Yeah, we're gonna see something with C2, right? So we have C2, and plus or minus? Plus, okay? And then I get over to here. What am I gonna have to see here? Minus I2, which is really I already said that I2 is I, times R2 is equal to 0. And then I already solved this equation I could solve for Q1, this equation I could solve for Q2. All right, I'm not going to spend time on the algebra, but that's pretty much it. Okay? So these, and you could have, if you hadn't seen what I had done here for this inner loop and this decoupled nicely, you could have done a different loop, and that's okay. It just would have been a little bit more complicated to solve in the end. Now, the thing that I want you guys to remember is that this is not an algebra class. It's not a class on solving systems of equations. So the most important thing for you to do is to obtain equations that can be solved. If this was a 25-point problem, I would say that just getting this equation, and this equation, consistent with the way that you define things here, would be somewhere between 20 and 22 out of 25 points, okay? So the last bit of points that you would get would be for solving the system, but that's less important than obtaining the equations that can be solved, okay? Other questions? Okay. Yeah.
Putting a third junction at the bottom, it's not going to change anything, right?
Right here? Yeah, so what you end up seeing here is it's redundant, because what it's going to end up saying is this is the I1, this is the I4 here. This one comes around to be I3 again. So you get really the same equation from this junction and this junction. Yeah. So that's another thing that you want to be careful of. When I say you need to draw 3 loops, they need to, or use 3 things to get 3 systems of, you have 3 unknowns, you need 3 independent equations, right? So when I say you do 3 loops, you can't do this loop and then do that loop, right? They are different in a sense, but they end up giving you all the same information. And that's what doing this would do for this. It's the same information, so it doesn't allow you to solve the system. But you could do this. You could do this. Okay. You had a question too, right?
I looked it up.
Okay. Anything else for this one? I want to, clock stop. I don't want to spend too much more time solving these myself. I want you guys to work on them. And I'll have the live stream tonight, so I'll do some more circuits for you to watch, but I do want you to practice it yourself a little bit more.